Hello everyone, welcome to this Men&Mice webinar. My name is Peter Petersson, and with me today I have Karsten Strodman from the Men&Mice Professional Services. Karsten, you're there?
I'm here, hello.
Very good. So today's webinar is focused on DNSTap. That is like a new technology on how to monitor DNS server operations. And so please note everyone that you are muted during this session, but you can submit your questions through the GoToMeeting control panel. We are also recording this session, and you can find the webinar along with the slides at our website within a few days. So at our website, you can also find recordings from previous webinars. So if you drop off this call, you can pick up where you left off by finding the webinar at our website later on. So having said that, Karsten, the audience is yours.
Thank you, Peter. Hello, welcome everybody to our today's webinar on DNSTap, a deeper look into DNS server operations. And we look at Unbound, Knot-DNS, and Bind. Just happened to DNSTap to land in Bind as well. So we'll show a little bit on that. But before we start with DNSTap, we have security issues, and we have a lot of them today. Just yesterday night, IC has published 3 security warnings for Bind, and the first one is for all versions, especially for Bind name servers running as DNS resolvers. That is, that are serving clients. There is a critical security issue where someone from the outside remotely can send a special crafted DNS query, and that will trigger a special assertion in the Bind code that makes Bind to terminate. So it's not possible for someone from the outside to take over the machine running Bind, but it's possible to switch off like Bind from the outside. And this should be fixed as soon as possible. We at Men&Mice, we are currently building new Bind packages for support customers, and you will find them even if you are not a support customer on our download site, packages.menandmice.com/bind. And the Unix and Linux distributions should have new packages out either today or in the remainder of this week. So this was the first one, and then there's a second one, which is not as severe as the other one. And there was a bug that was introduced in the last releases in 9.9.8 and 9.10.3. If you have older versions of Bind running, then you are not vulnerable to this issue, but maybe to the first one. And this can also cause the server to exit when it sees a special crafted DNS query. And related to Bind, not directly a Bind issue, but related to Bind, is because Bind uses OpenSSL for cryptographic operations, and the OpenSSL team just issued last week new security information, and you see the link here to the information. And ISC is highly recommending that someone who is running Bind should upgrade the OpenSSL installation on that machine and then restart Bind. And if Bind has been compiled manually with maybe linked statically to OpenSSL, then the new OpenSSL need to be built and linked as well. So if you have any questions about the security issues and you need help with any of that, don't hesitate to send us an email to support@menandmice.com, and we see how we can help you. So, but now to DNSTap. Now, DNSTap, what is it? It tries to solve an old problem, and that old problem is how to monitor what a DNS server is doing internally, to know what the DNS server is working on. A classic way to do that is query logging. People running Bind name servers know query logging. They can turn it on with RNDC query log, and that will write out every query that has been received by the name server to a file. Now, on busy name servers, this is difficult to do because it has a huge performance impact. We see about up to 200% performance loss when query logging is enabled. This is because two times. One problem here is that for every query coming in, the bind name server must construct a text in memory that is then been written out to disk, and allocating memory, concatenating the data in memory, and then writing that out to disk is slow. And then the query processing has to wait until the data is being really written to disk. So it's the speed of the disk storage which is the limiting factor here. And the same is true for other name servers like Unbound. You can also enable query logging in Unbound, and it has the same problem. And other name servers have that as well. It's just if you write to disk for every query, then you can only answer queries at the speed of your hard drive, which is usually much slower than a DNS server that just works from memory. An alternative solution that is being used for the last 15 years is to capture DNS traffic from the outside using a network traffic capture tool, something like TCP dump or something similar, using the PCAP libraries. The positive effect here is that there's no performance impact from the DNS server, and it's not even seen from the DNS server. It's purely on the transport way. The way to do this usually is to create a monitoring port on a switch where all the traffic that is being routed to the DNS server is also given out to an extra monitoring port on the switch, and there a special device is collecting the data from the network. However, doing this is difficult with UDP fragments because then the fragments need to be first collected and merged together, and also DNS data in TCP streams is very difficult to work with in this network capture environments. That's the reason why these systems, where they exist, they just skip the UDP fragment and the DNS data. Examples of tools like this are the Men&Mice DNS traffic monitor that works with a network probe, and also the open source DNS statistics collector from CADA, which is being used, for example, at the root server system. Now, DNSTap is a new technology that tries to solve these problems. Here, the events are not recorded from the outside, but they are recorded inside the server, but they are recorded in a way that it's non-blocking and has a minimal impact on the DNS server's overall performance. So it's a protocol that is designed to be very fast and lightweight, and it should not block or stop or make the DNS server slower in any way more than necessary. So here we have a graphic that shows how DNSTap works. DNSTap is deployed here on the DNS resolver, which is the box in the middle. We have a DNS client sending queries, and we have DNS authoritative server on the top. The client is sending a query to the DNS resolver, and because the DNS resolver has DNSTap enabled, DNSTap builds a ring buffer in the memory. And the ring buffer will take all the events from the DNS resolver. Now here the event that a client has just sent a query out to the resolver is being recorded in the buffer, and that is the blue part which is now in the buffer. So in real life, the ring buffer, of course, is much larger. It's not that 1/4 of the buffer is already filled with one event, but it's just here to make the point. Then there is a different thread that is a different part of the DNS server program, which is not bound to the DNS traffic processing. That I/O thread takes the data out of the ring buffer and writes that to a file. So that I/O thread can work completely asynchronously from the DNS resolving, can even on a multi-core system work on a different CPU core. So, and when it's once it's written out, the ring buffer is empty again. It's all green again. The resolver, in order to respond to the query from the DNS client, needs to do its own queries to the authoritative, to one or more authoritative servers. Here we see a query going out to the authoritative server. That query going out is also being recorded, goes into the buffer, and is then written to the file. The answer is coming back. Answer is coming back from the authoritative server and is given then to the client. Both these events are also written to the ring buffer and then written to the file again. The DNS resolver will also store this data in a cache, and with the DNSTap, it's even possible to observe cache events, like when is a cache entry actually be overwritten or deleted in the cache. That also can create an event and is then written to the file. This is something that has not been able to be observed without DNSTap. So neither query logging nor looking from the outside can give us any idea about the cache events. Also, traditional query logging also tells us the queries from the client, but not the answers that are coming back, and not the traffic that has been exchanged between the resolver and the authoritative server. DNSTap can give us the insights to all of that data. So we see the whole communication from the client to the resolver, from the resolver to one or many authoritative servers, and the data coming back from the authoritative servers, and the answer that is sent out to the client. So we have much more data compared to traditional query logging here. In case of an overload, here shown by a client that is sending a lot of queries, then the ring buffer has a finite amount of storage. And the events are then thrown away very early. That is, before entering the ring buffer. If the ring buffer is full and the I/O thread cannot write the data to disk as quick as needed, then if there's a new event that are to be stored in the ring buffer, but the ring buffer is full, that event is then lost. That is unfortunate, but it's much better than blocking the DNS resolver, which would happen in the query logging case. So even the queries are not blocked in any way. We are just losing some of the data that is being written to the file. DNSTap is an open technology that has been developed by Farsight Security, and Farsight Security is the company founded by Paul Vixie and colleagues, and Paul Vixie and Robert Edmonds from Farsight Security are working on this. There is a dedicated homepage on DNSTap, which is DNSTap.info, and you can find a lot of information, videos and slide material from both Paul Vixie and Robert on that slide. DNSTap is currently implemented in the latest versions of Unbound. So the latest version just out is 1.5.7, and it's in there. It's implemented in the Knot-DNS server from Zizitnik, and it will be in bind 9.11, which is the upcoming bind version that is scheduled for the first quarter of next year. And also DNSTap is being planned for NSD and is planned for the PowerDNS server. For all the supported DNS servers at the moment, that is Unbound, Knot, and also bind 9, DNSTap is a compile time option, because once DNSTap is compiled in the product, there is a slight, maybe 1 or 2% performance impact, because there's more code that needs to be executed for every query being processed. So not everyone wants to have DNSTap, so it's disabled by default. And if you want to use DNSTap, you have to enable it while compiling. At the moment, DNSTap is not enabled in any of the Unix Linux distribution package codes, with the exception of Gentoo Linux. In Gentoo Linux, you can set a use flag DNSTap that enables DNSTap compiling in. So if you're running bind or unbound or Knot-DNS at the moment, and you want to use DNSTap, you have to compile from source. We at Men&Mice considering making installer packages for Red Hat, Debian, and other operating systems available for both Unbound and Bind 9 containing DNSTap. If you are interested in seeing these packages, please let us know. And they will be then available for download at packages-menandmice.com/unbound and packages.menandmice.com/bind. DNSTap makes use of two external technologies. One is the frame-stream data transport protocol, which has been developed inside Farsight Security. It's a protocol library that puts data in frames, and these frames can then be sent over any kind of transport protocol. It could be a Unix socket, can be a TCP socket, can be anything else. It makes just sure that the sending side makes some frames, that is units of data that is being sent, and the receiving side then knows when it has received the full frames. The use here is to make sure that no incomplete data is being transmitted, but only full frames being transmitted. And the other dependency is Google protocol buffers, which is a way to describe structured data in a binary, very lightweight format. So think about XML, but XML is very bloated and text-based and usually slow. And protocol buffers is the same, but binary and quite fast. And it's being used inside Google for a lot of their services. So it's mature and it's been battle proven. DNSTap works with binary data because that's much faster than having the DNS server construct text strings and write that to disk. So instead of writing text strings, just binary data in the protocol buffer format is being written. So it requires some extra tooling to read these binary programs. And there are different tools available. There is the original DNSTap implementation in the Go language. There is a new one, which is now the reference implementation using the LDNS library, which is DNSTap LDNS. And coming with Bind 9.11, there is DNSTap-read, which will be part of Bind 9.11. And if you compile that version, install that version, it will be in there. DNSTap-read is the most advanced version of these read command line tools. And there's even a graphical fork of Wireshark that has DNSTap support. So instead of then opening PCAP files with Wireshark, you can direct Wireshark to open just a DNSTap file and then inspect the data in Wireshark. So let's have a look in how it works in the real world. So this is a very simple Unbound configuration with DNSTap, and the DNSTap specific part is here in green. So with DNSTap enabled, yes, we configure that DNSTap is enabled, and Unbound writes the raw data, the DNSTap data, into a Unix socket, and it then needs to be read from the Unix socket from another tool and written to disk. Now the socket here is /opt/dnstap.unbound, and it will also send the identity and the version. Identity means the host name of the machine running Unbound, and the version is the version number of the bind version. And with DNSTap log resolver response messages, we want to log the responses being sent from Unbound back to the client. And also with log client query message, we want to log the requests sent from the client to Unbound. Because Unbound only sends the data to a Unix socket, we need to have a tool to read the data from the Unix socket and write it out to disk. So this is the command. It's fstrm_capture, which is part of the FrameStream tool set. We have to give it the information which protocol buffer format's being used, which is the Unix socket to be read, and which file to be written out. And the -D, this is just the heavy debug output. And once we've done that, we have a file, and then we can read the file, for example, with DNSTap-LDNS. Because DNSTap is an open technology, you can read the binary files with any tools that understand DNSTap. So you can also use the bind DNSTap.read to read a file that has been written by Unbound, and you can mix and match the toolings from the different DNS servers. So let's have a real-world demo here. So here I have a session into a Linux server, which is a Fedora server, and on the top I will start Unbound, which has the configuration like I've just showed you in the slides. So I'm starting Unbound 157 in the foreground. Then in the middle, I will start, at the first down there, I start the form string capture. So it reads from the socket from opt DNSTap.unbound, and it writes to opt unbound.tap. So it's listening there, and Unbound now has detected that something is listening there and made connection. And we see that in the debug output that we already see the first streams appearing. And now I do some digging to my local loopback address, and I ask for Men&Mice.com, and the answer is coming there. And we just seen here in the FrameStream output that it has processed a data frame that was 136 bytes of size, and that was the data being created by the dig I just done. So I'm doing another dig for a domain called DNSSecWorks. And here we also say a new frame has been processed. And the third one, let's do for info.men&mice.com. We have another frame being processed and being stored. So now I'm stopping the frame stream, shutting that down, shutting down my DNS server, and I'm zooming into the middle shell here. And if I now look at the OPT directory, I have a unbound.tap file. Here, which is the binary file being written. The DNSTap.unbound file that we see on the top here, this is the Unix socket that has been created and being used in the communication. And now I can use the LDNS read the DNSTap LDNS reading the unbound opt unbound.tap, and it gives me an overview of what is in the file. I see the timestamps. I see here a two-letter abbreviation of the data being stored. CQ means client query. I see the IP address that made the query, which is the loopback address. It was a UDP query, and there are 43 bytes being stored. It was for Men&Mice.com, and it was for an A record in the internet class. Now that's an overview, and with LDNS, with DNSTap LDNS, I can specify the -y switch, and -y will print out the detail information in YAML format, which is a modern structured text format for displaying data, and that can be used or read in then by different scripts. So you can use Ruby or Python or Perl or PowerShell to work on this data. And here we see all the data that is being stored in that file. We see the version number, we see the identity, and we see the message here, including all the different sections from a DNS message. So next, I would like to show you the Knot-DNS server. So this is the configuration file for the Knot-DNS server, Knot being an authoritative server. This is the DNSTap configuration. Knot can write the DNSTap information directly to a file or to a Unix socket. To make it easier here, I'm writing directly to a file, which is opt.knot.tap. And in the template, I've specified that for all zones, I want to have a capture all, that is all traffic that is going to all zones should be captured. It is also possible to enable DNSTap capturing for specific zones only. And there's just one zone in this configuration to keep it simple, which is the example.com zone. So I'm starting the Knot DNS server here, and it's now running in the foreground. I'm switching over to the other shell. And we already have an empty DNSTap file here being created. Now I'm sending some dig queries to Knot, asking for example.com SOA record, and I get an answer back asking for the NS records. Yeah, there are some NS records. I'm asking for an A record. No, there is no A record there. I'm asking for the www name, and there is no name. So now we already have a few queries towards the server. I'm going up and I'm stopping the server. And if I now look at the OPT directory, the knot.tap is being filled. And I can use again LDNS read, DNSTap LDNS to read. -R, giving the file. And the same as we have seen with Unbound here. I see the queries in here. But these are not of type QC or CQ. These are AR. So CQ was client query, AR is authoritative response. So here's a slight little bug in the output, which is in the Knot-DNS server. Need to open a bug for that, because what we see here actually is the client query coming in and the answer going out. So the first one of every tuple should be a CQ of type CQ, and the other one is then the response. So we see here the request for the server coming in. The request was 92 byte, 29 byte, and the answer was 92 byte. And again, here I can go to the YAML output, and I'm piping this here into the less pager. And here we see now the original query coming in. So this type here on the top that's wrong. It should be a client query. But we see the query, it was for example.com SOA record. And then down here, we have the authoritative response, including all the response data, which is something we don't have in case of query logging. And it goes on with the other queries. So here was the query for the NS records. And we see the whole data, including header, eDNS0, and additional and answer section. And that was DNSTap in the Knot-DNS server. And now we're looking into bind. And the bind configuration, I have just a very simple DNS resolver configuration here. There is a DNSTap block in the option block where you can specify what kind of request you want to capture with DNSTap. Now I have configured here all, but it also would be possible to have a client, authoritative resolver, and forwarder information. And all these four different selectors, you can also specify then query or response. You can have like the client queries and the authoritative responses, or the resolver queries and resolver responses, and so on in there. DNSTap output file is the file to be written. The DNSTap identity is the host name of the machine, and the version in this case is bind 9.11 development from the Git source. And we want to have DNSSEC validation in this case. So I'm starting bind here in the foreground, and it started, and we see in the log output it's opening a DNSTap file. And now I send some queries like I've done before, men&mice.com. We'll get an answer here. I'm asking for DNSSEC works, and that has been authenticated, so it took a little bit more time to fetch all the DNSSEC data, and we ask for info.men&mice.com. We get that data back. So if we now look in the OPT directory, we see a bind9 file, and we see it's much, much larger than the file that is being created by Knot or Unbound. The reason here is that bind is storing much, much more information, especially because I have selected to write everything in the DNSTap. It will write all the communication it did with the root name servers, with the top-level domain servers, everything the resolver did, everything is there in the tab file. You see really the whole communication of the bind name server, which is very, very powerful. And now I will use the tool that comes with bind to read this file. For that, I zoom into this screen here, and I'm using the tool called DNSTap Read. And first I give it the file, and without any other selectors or options, I see the different queries and responses being made here. And we see this is the original query I've sent. It's a client query. And then that triggers a resolver query. So that's a query being sent out by the resolver to an authoritative server. And here is a response that it has received. And it goes on, and at the end there's somewhere the data being sent to the client. So it's much more data. There is an option -P and -P will print out the package data for every entry. And also I'm piping that here to less because it's a lot of data. And now here we see here what is being requested. And in the beginning we see it's a lot of priming, so asking for the DNS key of the root name servers, asking for the NS records of the root name servers, receiving here an answer of the root name servers, receiving answers of the DNS keys of the root name servers. I'm going a little bit down. Now this is all priming, looking for info.men&mice. So here it starts with the request for info.men&mice.com, and we see the answer was a CNAME, and then worked on the CNAME stuff. And we see it's very detailed. It's a lot more information than we had with the classical query logging. And of course, the same file can also be read by the other tools. -R in the file. So this is the same file being seen by DNSTap -LDNS. So I'm skipping now here the slides that explain the configurations. This is basically what I've just shown you. So in summary, DNSTap is a new and open standard for how to monitor and look deeper into what a DNS server is doing. And it's designed especially for large and very busy DNS servers. So it's because query logging is not a problem if you have 10, 20, maybe 100 queries per second. But if you have 20,000 queries, 400,000 queries per second on your resolver infrastructure, if you are a large telco or DSL provider, then it's very difficult to use DNS query logging at all, and DNSTap helps here. It has a minimal performance loss. There is a little performance loss, maybe 5 to 10% max, but not so much. Much less than with the query logging. And what's nice here is it sees wide adoption among open source DNS servers, and there is the hope that once the open source DNS server world has adopted DNSTap, that also commercial vendors like Microsoft, for example, will also implement DNSTap in their products, so that the same tooling can be used across all the name servers. So, our next webinar will be on Windows, the new Windows 2016 DNS server. We will talk about all the news that are in there. We will do a demo on the latest beta of Windows 2016. And then in February, we'll have an update on DNSSEC and DANE. What's new there, new implementations, what's new in the market, new deployments, and the status of the Internet standards. So, Peter, do we have any questions?
Yes, Carsten, we do indeed. So I have a question here from Carlos. When using like an Unbound DNS server, can we have more details on the query log? For example, like a client IP source, used flags, etc.
Yes, that's all in the data. So that's in the DNSTap data file. It's just a matter of using a tool that reads the data out and makes it visible. So DNSTap LDNS can do that with the -Y switch, which shows the flags, shows the client IP source, or the DNSTap read from bind does that as well. So even if you're using Unbound and you're using DNSTap with Unbound, you can use the bind tool to make the file visible, because the bind tool is currently the most advanced one in the way how it shows the data.
Very good. So, Carsten, apart from the government spying up on us, what other use cases do we have? How does this help? What problem does it solve? Can it give us like a use case of all this, seeing all this DNS traffic there?
It's of course a great troubleshooting tool. If some client reports a problem resolving a name, and the operator of the DNS server needs to find out, okay, where is it really failing? Is it something in the cache of my DNS resolver that is just wrong, or is it some request that goes out to the authoritative server that gets the wrong answer in? This is something that can help. It can also be used for creating statistics, something that we've done with the Men&Mice traffic monitor. So knowing what is being queried, what names, what record types being queried, that can be used and create nice statistics out of that.
Yeah, that makes sense. So
about the government spying, Paul Vixie, I've just watched a video of him explaining DNSTap the other day. He said that DNSTap as a technology is less prone to be misused compared to the older network capturing method, because this system here at least requires consent with the operator of the DNS server, while watching on the network, everyone can do it with access to the network. So if an agency has access to the wires, they can just wiretap and see what's going on there. In order to use DNSTap, you need to have control of the DNS server, enable it there, and then look into that. Of course, it still opens up the possibility that some operator looks at the data of his clients, but that should be then something in the trust between the operator and his clients.
Okay. So one more question, a question from Jan. Are there any tools to perform analysis such as top 10 queried domains, top 10 clients, possible DNS exfiltrations attacks, etc.?
There are these tools, but they are currently not public. So certain people have written these kind of tools for their own use using DNSTap, but I haven't seen like an open source public version of it. Yeah, it would be nice to have that. I have that somewhere on my to-do list, but my to-do list is quite long, and I'm not sure when I will be able to work on this. For example, it might be nice to have a DNSTap module for the Men&Mice traffic monitor there, which does exactly that: top 10 queried domains, top 10 clients, or have something like DNSTop working on DNSTap. So yeah, I'm not aware of any open source free available tools, but it should be quite straightforward with the existing tooling to write just a tool that shows the top 10 domains, top 10 clients, tagging patterns.
Okay. So let me see. We have one more question from Carlos. What is the need in memory to have this tool working on a busy CAS servers?
Not much memory, because there's the ring buffer, and that is a fixed amount of memory. I haven't really looked into that, but it's not that big, maybe 10 megabytes or so, and that is fixed, so it's not growing with the amount of data that is going through the server. It is just if the ring buffer is full, events get lost. So, but that is a trade-off. We want to have we have a trade-off here that we want to lose events instead of making our DNS server slow. But apart from this ring buffer that is being allocated in the beginning and is just a fixed amount of memory, there's no extra memory being used. And this is or was a special design criteria for DNSTap, is that it's not doing memory allocations while it's running. It does one upfront memory allocation, and that's it.
Well, that sounds like good engineering. So I don't see any additional questions here, so I would just like to remind everyone to sign up for our webinars in the coming weeks and months. So, Karsten, thank you for an excellent webinar, and everyone out there, thank you as well for attending, and happy holidays.
Thank you. Happy holidays.